Good morning, everybody. We're going to start today by talking about orbitals. So, in the Bohr model, we kind of had just discrete energy levels, and that works pretty good. But it doesn't actually describe the patterns of probability of where we will find electrons, because of that uncertainty principle we kind of worked through last time. We saw that, generally speaking, we have no idea where electrons are within an atom exactly. But we do know, based on various mathematical models, the probability of finding an electron in certain areas. And so that takes us into the quantum mechanical model, which instead of just having rings like these to indicate energy levels, we have more. We have different things happening. We have some patterns that look like spheres. We have some patterns that look like dumbbells, some that look like little clover shapes, or even these like flowery looking things. We're going to see that instead of just having circles, we're going to have different patterns of probability of how likely it is to find an electron. And instead, we call these orbitals. This was orbits in the Bohr model. We just have like a planet. We have orbits around things, or the sun, I suppose. And only the moon orbits the Earth. Well, I guess we have a lot of satellites, but uh, that aside, we're going to see that we actually have a better way of describing how these work. And suffice it to say that we're going to have ways of talking about all these different orbitals. So the first thing we want to describe is kind of the idea of shells, right? In the orbit model, we had n=1 and n=2 and n=3, and these were just kind of orbits, right? They were levels around the nucleus. And we're going to see that we typically go all the way to 7. Guess I can't just go to 7. I have to include the 6 and 5, don't I? And these correspond with periods on the periodic table. In theory, yes, we go to infinity orbits, but those are only for excited states. So when we're looking at ground states and where we're going to typically find electrons in atoms, they're going to be somewhere within one of these 7 shells, as we call them. So these are called shells. And these are kind of just groups of orbitals. And we see that as n increases, we go farther and farther from the nucleus. Farther from the nucleus. We call n, by the way, the principal quantum number. And we're going to see that we can use a set of quantum numbers to talk about any specific electron we want in an atom. And so our first one was talking about the principal quantum number, which shell that those electrons happen to be in, or that one. Excuse me. And we're going to see that as we go farther from the nucleus, we kind of talked about this on Tuesday, but the farther you go, the higher energy you go as well. And so as n increases, the energy also increases. And we also know in chemistry, as always, we always want to form our most stable form, right? We want to always be as low energy as possible. So that's kind of the last little bit here. Just remember, everything in chemistry wants the lowest energy possible. And of course, I mean, I don't mean to anthropomorphize. I don't mean to say that electrons are alive and have wants and desires, as far as I know. Um, but what I mean by wants is just, as things react, they all tend towards lower energy. That's just happens to be the most stable place for electrons to be. And so we're going to see that everything wants to be as low as possible. And it makes sense, right? Electrons would want to be closer to the nucleus because it's positive, they're negative, so they would want to be as close as possible. All right, so we're going to see that that's our first kind of quantum number. And we're going to see that in each quantum number, each principal quantum number level, each shell, we have a certain number of subshells that make up that shell. And we're going to see we have another quantum number to talk about the subshells. We're going to see we have the quantum number L. Will tell us the subshell. And that's kind of which probability. And we're going to see that L goes anywhere from, for a particular shell, it can equal whatever shell that is minus 1, any of the numbers equal to that. So I should just, let me put a range here. So L goes between 0 and n minus 1. So let's take a look at some values for L. For n equals 1, L has to be between 0 and 1 minus 1, which is 0. So L can only be 0. For n equals 2, L can be 0 or 1. For n equals 3, 0, 1, or 2. And for n equals 4, guess what? We can go up to 3. So the higher shell we're in, the more subshells we have available to us. And we're going to see that these correspond to the orbital shapes, or as we call them, the kind of probability distributions. And as I mentioned earlier, we kind of have four main ones. We have spheres, we have these little dumbbell things, we have these clover shapes, and then we have some like flowery things. And these correspond with certain values of L. This one is L equals 0. This is L equals 1, 2, and 3. We also use letters to describe these. These are s orbitals. These are p orbitals, d orbitals, and f orbitals. And these just are certain shapes that the probability of finding an electron happens to adopt. And so for something in an s orbital, that happens to be a spherical distribution. If it's in a p orbital, you have an equal distribution of kind of being on top of this shape or on the bottom. And then with D, you just have even more options, and F, you just go crazy. So there are other shapes. These are just representative ones. and we're gonna look at some of those in a little bit. But suffice it to say, so far, what we can see here is that for the first quantum number, we only have the spherical distribution. So things are only distributed in a sphere around. And for the second one, we have both the sphere and the dumbbell shape. For the third principal quantum number, we have the sphere, the dumbbell, and the clover. So you see, we just keep adding them. And so this L number represents the shape of the probability that's being formed. We have more. I'm going to copy this just so I have more room to work with this. We have a third number. We're going to have 4 total numbers, by the way. But we're going to see that special combination, or each combination of these will allow us to talk about very specific electrons. So we can talk about one electron at a time. This next one is called ML, M sub L. And the value of this goes between minus L and plus L. So M sub L has values between minus L and L, positive L. So for L equals 0, ML has to be between negative 0 and 0, so it's just 0. For L equals 1, ML is negative 1, 0, or 1. If L, so I should redo this chart actually because we're going to get too many things here. So that in mind, for L equals 0, L equals 1, L equals 2, L equals 3, we're going to look at these specifically because L tells us the shape. We're going to see that ML tells us how that shape is oriented. So for L equals 0, for s orbitals, we only have one orientation, and it's a sphere, right? Doesn't matter how we turn that sphere or tilt the sphere, it's still a sphere. So it doesn't quite matter. We're going to see that for the p orbitals, we're going to have 3 different ways of orienting those. For L equals 2, we're going to have 5 different ways. We have 5 different options. And then with L equals 3, we have 7 options. And we'll see what all those look like right now. So for L equals 1, those are p orbitals. Those look like the dumbbells. We're going to see that we have 3 different kinds. We have the vertical one, the horizontal one, and the one that goes kind of in the plane, or it's like coming in and out at us. So we have one oriented along the z-axis, up and down. We have one along the x-axis, that's left and right. And then we have one along the y-axis, which is back and forward. So if you think about 3-dimensional plane, xyz, those orbitals line up with those 3 directions. And so these are the 3 orientations that would go with this. I must say I don't quite remember which one is which. That doesn't really matter right here. But these are what these these ML quantum numbers stand for. They tell us which direction those orbitals happen to be in. And we're going to see that those could be in any of 3 directions. And so electrons can be found in this PZ where they are in probabilities going up and down in this dumbbell shape. They could be in a px, which means their probability is looking like an infinity symbol, and then they could be oriented in the y direction as well. So we have three different options for p orbitals. And then for d orbitals, I'm not going to draw the F here. You know what? I'm gonna show you the d orbitals on Google. It's just going to be a lot nicer. There's four of them that look very similar, and there's going to be one that is different looking. So let's take a look at these. So let me hop over to Google here so we can see. Let's look at some d orbitals. D orbitals are special. Let's see if you can't find some nice looking ones. Yeah. These are the shapes of d orbitals. So we have 5 different kinds, which our ML numbers suggest. We have 2 that are kind of in this XY plane, one that's in between the X and Y's, one that aligns with the X and Y's. And then we have the same thing for the vertical plane. We have ones that align with y and z axes, and then x and z axes. And then we have this weird one. We have what looks like a p orbital with a donut around it. And so we see that all of these are options of probability of where we might find an electron. And this is actually a pretty cool image right here. This is what it all looks like when we put them together. So instead of having nice rings around our atom, we actually have all these lobes everywhere. And this is just the D subshell of one particular shell. So as you can imagine, it's much more complicated than simply just rings around an atom. So we have all these different lobes. And I'll show you the f orbitals. We don't really need to focus on these too much, but this is what f orbitals look like. Down here, there's these flower shapes. There's this weird double donut thing. I don't even know what we describe this as, but we can see different shapes of f orbitals. So suffice to say, the f ones are a lot more complicated. We're not really going to look at these very much, but this is what they do look like. So these are the probability distributions of finding electrons in F subshells. Okay, so back to this though. These correspond with the orientations of these orbitals. And so we'll talk more about d orbitals in next semester. F orbitals we're not even going to touch. But mostly in this class, we focus on S and P orbitals. And in organic chemistry as well, we focus on S orbitals and P orbitals. So I'm happy if we just know these shapes for now. So S orbitals, again, just a sphere. All right, and so we don't have any options of orienting that sphere differently. All right, we have one last quantum number, and then we'll see what the point of doing all this is. The last quantum number is M sub s, and thankfully this one only has 2 values. So we saw that, ML, we can have values depending on what L is, so anywhere from minus L to positive L. L can have anything between 0 and n minus 1. L can have anything from negative L to positive L. MS can only equal a half or a negative 1/2. So either positive or negative. And this refers to kind of the spin of the electron. And what this means is you can think of it as spinning. One of them is spinning clockwise. We'll say the other one is spinning counterclockwise. It just so happens that we can accommodate 2 electrons in every orbital. And one of them is going to be spinning in one direction, the other one will be spinning the opposite direction. So just accept that, I suppose. And so we can kind of use this information to talk about various um, subshells. So we might describe these as boxes. We might describe these as boxes. So we have our three p orbitals. If we were to describe a d orbital, we've got 5 options because that's how many um, ml numbers we had for L equals 2. Don't forget this is L equals 0, L equals 1, L equals 2. We had xy, yz, xz, x squared minus y squared, and then z squared. You don't need to know those names, but suffice it to say these are the 5 d orbitals. These are the 3 p orbitals. And then you have 7 f orbitals. I'll just write that. 1, 2, 3, 4, 5, 6. That's probably about right. The f orbitals. What this means is that we can put 2 electrons in each box to describe how those electrons are working. So we put one arrow up for the first electron, and we can say that that one has a spin of positive 1/2. The other one we put upside down, and that's the one that's going to have a negative spin. So it's a way of, for us, being able to describe where electrons are within an atom. And, sorry, 1 second. Might sneeze? Nope. Okay. With these, we're going to see, though, that we can talk about all the electrons in a given atom. We have a lot of information here. I get that. And there's still a lot to go with this. But suffice it to say, knowing all these numbers, we can identify any electron that we want to talk about in test. Okay, let's try that again. Interest. And so we're going to see that we can talk about all these electrons very nicely using the periodic table. But let's take a look at the periodic table. The periodic table here, and I'm going to put our blob at the bottom. We're going to see that the periodic table, the way it is organized, also is in terms of these orbitals. So originally it was designed because things in the same group have similar properties as each other. They react similarly. We're going to see that the reason for this is because their orbitals are analogous to each other. And we'll see what that means in just a little bit. Suffice it to say that this periodic table is really divided into sections. We know that the principal quantum number generally refers to the period of the periodic table. So that goes from 1 to 7. That is our principal quantum number. It talks about the period on the periodic table. We're going to see that our L's, remember the orbital, we're going to see that certain areas of the periodic table are kind of defined by their orbitals. we're going to see that this section is going to be called the S block. We're going to see that those two columns are defined by their s orbital. On the other side, we have the p block. Everything in this group will be defined by the p orbital. Not this one. This one's still s. By the way, helium, still s. We'll see why that is. If we keep going, we're going to see that the transition metals are defined by d electrons, and then the rare earth metals are, or the inner transition metals are f electrons. And we're going to see ways of talking about all of these. So far, are we, I'm sure, confused, but don't worry, there are patterns here that we're going to see. We're going to see the periodic table can tell us everything we need to know about electrons in an atom. And so we're going to see that this is a nice way for us to organize our ideas about electrons just using the periodic table. So understanding these blocks and the idea of the period is going to be very useful for us. So let's take a look at what we might do. So we saw that we have all these different principal quantum numbers. These are rows of the periodic table. We saw for n equals 1, we only had an s subshell. For n equals 2, we had s and p subshells. And as we keep going on the periodic table, we keep adding more. Suffice it to say, we describe these by using their quantum number, or I'm sorry, their principal quantum number and their orbital letter. So in the first shell, we have a 2s orbital. I'm sorry, in the first orbital, first shell, we have the 1s orbital, and that's it. There's no other things going on there. In the second shell, we have the 2s orbital and the 2p orbital. And in fact, there are 3 of these. Remember that for p orbitals, we have 3 different ways of orienting them. We have them orienting in the x-axis, the y-axis, or the z-axis. For the third one, we have the p orbitals, the s orbital, the p orbital, and now we have a d orbital as well. And remember, with d orbitals, we have 5 d orbitals. And let's just go up to 4 because that's usually as far as we go in terms of all these orbitals. We're going to have a 4s, a 4p, a 4d, and a 4f orbital. Remember, we have 5d orbitals, we have 3p orbitals, and we're going to have 7 f orbitals in various different directions. What that might look like for us, if we just kind of write all these out, we'll see that we can arrange them from low to high. And in fact, this is what we're going to see is the kind of lowest energy as our closest ones to the nucleus, and these will be our higher energy ones. where these electrons happen to be located. And we're going to see that the more electrons we have, the more of these boxes get filled. And we're going to see that we can look at some of these. I'm going to just copy this because we'll use it a few times here. If we look at just hydrogen, just looking at hydrogen, it has just one electron, right? Hydrogen atom is one proton, one electron. If we are going to put that electron into a box, we always want to fill our lowest boxes first. Ta-da! And so this would be what's called the electron configuration for hydrogen. And we would describe this as having one electron in the 1s orbital. Right? We always want to give them the lowest energy possible. This is something called Hund's rule. You don't need to know that. But suffice it to say, we always fill them from the lowest energy orbital first, because that's where they would want to be, right? We're going to see that the more electrons we have, things get filled up. And once they're filled, we can't put any more in there. So we'll take a look at what happens with that. We're going to see that with helium, we have 2 electrons. Here's our set of boxes. We're going to fill them like so. And so we'll say that this is 1s2. This would be its electron configuration. If we go to, let's say, beryllium, I'm going to just skip ahead. We've got 4 electrons. If we're going to fill these orbitals, we would do this. We would fill them from lowest to highest, right? So we'll fill the 1s first and then the 2s. We would describe this as 1s2, 2s2. We have 2 electrons in the 1s orbital, 2 electrons in the 2s orbital. Let's look at nitrogen now. Nitrogen has 7 electrons. Skipping ahead, right? We don't need to do every single atom at a time. We have a couple options here. We can, that's 4 electrons we've taken care of. We have 7, so we could do 5, 6, 7. Or we could fill them separately. In either case, our electron configuration is 1s2, 2s2, 2p3. We combine all the p orbitals in one when we talk about the configuration. And we're going to see that we're not going to do it this way. We are always going to do it where we don't pair off electrons unless we have to. So we're going to see we fill equal energy orbitals singly, and then we start pairing off. So we fill them one at a time, single electrons, and then after that, once we have kind of half filled our orbital, then we start pairing them off and doing the upside down electrons. The downward arrow. And we have a special word for this. Equal energy. This is the word degenerate. Degenerate in kind of lay speech means, like a delinquent or someone not not doing well, someone doing bad things, perhaps. And that's not the definition for chemistry. For chemistry, that means equal energy. So there is no energy difference for an electron to be in px, py, or pz. Doesn't matter. They're equal energy. And so we describe those as the boxes. And so we'll fill them each singly, 1 electron per, and then we start pairing them off afterwards. So if you go to fluorine, fluorine is 9 electrons. Let's take a look. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So do we see how I did that? Where we put the first 3 in our p orbitals singles, and then we start pairing them off after that. And we would describe this, by the way, as 1s2, 2s2, 2p5. Because our p orbitals are degenerate, all 2p orbitals have the same energy, 2px, 2py, 2pz, all equal in terms of energy. We can clump them together. So we say 2p5. We don't need to say 2x2, 2px2, 2py2, 2pz1. There's no reason for that. So we just say 2p5. All right, and this is all well and good for relatively small numbers of electrons, right? 9 electrons, whatever, no big deal. We can get through that. But once we start talking about things with like 37 electrons or 53 electrons or whatever, it's a little tough to do something like this. And so we have ways of getting around this as well. So let's talk about that periodic table again. We're going to see that things where they are on the periodic table will tell us what the electron configuration is. For example, if we see fluorine right here, we're going to see that we found its electron configuration to be 1s2, 2s2, 2p5. What all that, like how to do that from the periodic table. The easiest way to do it is to look at where it is. Fluorine is in the p block. It's in the p block. And that's going to tell us that the highest energy are in a p orbital. And specifically because fluorine is in period 2, they're going to be in the 2p orbital. And we're going to see that all of these kind of sections of the periodic table correspond with particular orbitals. So don't forget helium is still part of 1s. It's a separate thing. So we're going to see that if we want to figure out fluorine's electron configuration, well, all we need to do is first look at where it is on the periodic table. We see it is going to be in period 2 in the p block. So that tells us we're going to have our last energy, our highest energy electrons, our last electrons in the configuration are going to be in 2p. And we just need to see which column it is in the p block. It's in the 5th column of the p block, and so it's going to have 5 electrons in the p orbital. So we have all these bits coming together. The 2, it's row on the periodic table. The p, because that's the block it's in. And then within that block, it's in the 5th column. We're going to see, there's 2 columns for the s. And guess what? We can fit 2 electrons in an s orbital. There's 6 columns in p. And guess what? We can fit a total of 6 electrons in a p orbital. 2 electrons per. Remember, we could have the positive spin or the negative spin electron. And we have 10 for the d. And we're going to have 14. I'm not going to draw it. We have 14 for the F block. And we're going to see that by looking at the position of something on the periodic table, we can figure out its electron configuration without having to do all these pesky boxes. And so it's a little bit easier this way. If we want to say, okay, well, what about chlorine? No, let's not do chlorine, let's do sulfur. And let's do it using the periodic table. Excuse me. I'm going to redraw the periodic table. We do that a lot in these 2 chapters. Okay. So we are going to see that we have some things here. Sulfur is right here. It is in the 4th column. It's in the 3rd row. And it's in the P block. So that tells us sulfur's last electrons, it ends in 3p4. So 3p is the 3 is the principal quantum number, that is the row on the periodic table. It's in the p block, and it has 4 electrons in the p shell. We know that because it's the 4th column in the p block. And so, if we want to think, well, everything else is lower energy, right? Go up to our boxes. 3p is the last ones we've drawn. Those are the highest energy. So it means that everything before 3p must be completely filled. Everything else must be completely filled. Because remember, we always fill lowest energy first before moving on to higher energy ones. So we just need to take a look and say, okay, well, there's 3p. Let's see what comes before it. So we see before 3p, here's 3p. Before that, we had filled our 3s subshell. So we need to then think, how many electrons can an s orbital hold? Well, it's only just got the one box because there's no other way of orienting a sphere. So s holds 2. And notice in the S block, there's only 2 columns. And then if we think, okay, well, that leads us here. Where do we fill before 3s? Well, if we go backwards, we see, that's right here. We had filled 2p before that. And understanding that p orbitals can hold a maximum of 6. And since this must be completely filled, we have to have 6 electrons there. And as we keep going backwards, we see we did 2s before that, and before that we did 1s. You can also start at hydrogen and just keep going across until you get to 3p4. That would work too. And so this would be its electron configuration. We just have to see what we cross through as we're going from hydrogen to sulfur, as we keep adding electrons in until we have however many, 16 electrons? Yeah, 16. Without having to worry about boxes or anything like that. So it's an easier way to do it. Any questions so far on this? All right. So if everything, we're going to see that works. Okay, cool. So if we look at the periodic table again, periodic table tells us our electron configurations. If we just label all of these, we can do that. S and P are easy. But we have a problem here, right? Because when we did this earlier, we said, well, wait a second, for n equals 3, we had L could be 0, 1, or 2, which is S, P, and D. Where the heck is the 3D? Well, that one is right here. It turns out that the D orbitals are in between the energies of the next shell's S and P orbitals. So we're going to see we start, if we go from 4s, then we drop down to 3d, fill that up, and then start filling in 4p after that. So 3d is in between 4s and 4p. 4d is between 5s and 5p. So as we're looking at this, the d orbitals always have one lower principal quantum number than their actual place on the periodic table, right? We know that we have these numbers corresponding to the rows, but for d orbitals, it's one less. So s and p orbitals keep the same number as their row on the periodic table. Potassium, 4s1, it's right there in the fourth row, in the S block, first column. However, we're going to see that because the 3d orbital is in between the energy of 4s and 5p, we always want to fill them in energy order. So we don't fill 3d after 3p, but we fill it after 4s. And the pattern is the same for all of these. And with the F block, don't forget right here is where the F block starts. Those actually, we start with 4f and 5f. Those are 2 lower than the quantum number that they are in. Remember that if we don't take out the F block, we technically need to go all the way down. This is where the F block technically goes, remember? So, oh my gosh. 2s, 3s, 4s, 5s, 6s, 7s. This is 4f right here. It comes after 6s. And we have our D ones here. And then our P orbitals. 2p, 3p. I missed one. 2p, 3p, 4p, 5p, 6p, 7p. So D1s have n minus 1 as their kind of principal quantum number. So their row on the periodic table minus 1 is the shell they're part of. And for F, it's n minus 2. For S and P, they are just the same as their um, their row on the periodic table. But let's see what this looks like. What does this actually mean for us? Well, let's look at something like, what should we do? How about arsenic? Let's not do arsenic. Let's do rubidium. Let's do rubidium. Because I don't want to keep putting us in the P block. Rubidium is right here. 5s. And it's going to have one electron in 5s. And we see that because it's in the first column of the s block. So we know it's last electrons. So we just need to fill up everything before that. This time I'm going to start at the start. Let's start with 1s. This will take us from hydrogen through helium. We start here at the very start, and we're going to go through the periodic table. So we're going to go through hydrogen and helium. Now we're going to start at 2s. And then we go across to 2p. We're just going to keep filling everything maximally until we get to 5s, because we know everything before 5s is completely filled. So we have 3s next, then 3p, and now we have 4s, and now we have 3d. So don't forget, as we go along this periodic table, it's terribly drawn here. It's terribly drawn, but in theory, this is the row that we're going on. Definitely an angle there. We're going to go now 3d. Don't forget there's 10 electrons that can fit in the D subshell. We then go to 4p and then 5s. Let's do this on the periodic table itself, so we can actually draw things nicely there. All right, so once you find out where it ends, where your element is on your periodic table tells you what the last electrons are. We just fill everything else before that completely. Let's take a look at the periodic table. And I'm going to just do a screen write on this. Okay, so I don't know why it always does this. Can I make this bigger? No. But suffice it to say, okay, I need a better color. How about green? Let's see if this will be better. Nope. How about yellow? I need something that's going to like overwrite this. How about like bright pink? Is that visible? No, not at all. Okay, how about white? Kind of. We're going to see that 1s, 2s, 2p, 3s, 3p. I don't know if this is visible at all. It kind of is. Oh, well. 4s, 3d, 4p, 5s, 4d, 5p. So remember that your D block, you use one less than the row it is on the periodic table. So even though it's row 5, we still say 4D. 6s. Then we actually have to jump down a little bit to 4f. Go through all that. Then to 5d, 6p, 7s. Although I don't have it here, we have 5f below that, which then goes up to 6d all the way to 7p. And that's as far as we go. So that's the idea here, is that you can just follow the periodic table and that will tell you what your electron configuration is in the correct order of energy. So just keep all of this in mind when you're doing them. I'm going to show you all a shortcut as well, but we just need to remember this as we go through the periodic table, that the d orbitals are 1 less and the f orbitals are 2 less. So I'll leave that up for just a second. But that's what we're looking at here. So in a correctly drawn periodic table, something that I'm incapable of doing, as you saw, it should make more sense as to why when we had 5s for rubidium, when we looked at this dude here, we had to fill the electrons in the order we did. So we started with 1s, then 2s, 2p, 3s, 3p, 4s, 3d, 4p, and then 5s. So we just have to keep filling up as we go. Right, but okay. But we have a shortcut. So our shortcut is we can say that we're going to kind of make a determination of a place to do our shortcut. And that is going to be using noble gases. If we take a look at rubidium, we see that all this stuff here that's in period 4 and below, this is the same as the noble gas configuration of krypton. All of this is krypton's electron configuration. And how do we know that? It's because, well, krypton is right here. It's the noble gas that's in period 4. And we know that since it's in the 6th column, it must have a full p subshell. And so, as a result, we can just say, okay, well, it's got krypton's electron configuration for all of its lower energy stuff, and the higher energy stuff is just everything that's not krypton. And so we might say, for this one, it's krypton 5s1. Makes it a little easier, right? We don't have to worry about all these SPDs, blah, blah, blah. We can just say, well, it's the same thing as krypton if we just add a 5s1 to it. And we can use this for other things. We can say, okay, well, I want to look at what about, I don't know, how about I want to do barium? Let's find barium on the periodic table. Barium is right here, number 56. Oh. Nope. Okay, barium's right there. It's in the 6th row. So if we look in the 5th row, our noble gas is xenon. The row before it has xenon as its noble gas configuration. So we could say, okay, well, we're just going to say everything xenon is, and then whatever barium is that xenon isn't. So starting at xenon, that takes us through 5p6. And we could say, oh, well, barium is just 6s2 after that. And so we could say, aha, well, it's just xenon's electron configuration and then 6s2. So start at your noble gas and then just go whatever else you need to do. If we're looking at lead, we'll see that that's also xenon, but we have 6s2, 4f14, 5d10, 6p2. So we still have to keep in mind all that stuff before. Lead's over here somewhere. That's an ugly lead, but lead is somewhere right there. So we still have to go through all the lower energy ones. We still have to go through 6s, 4f, 5d, and then 6p to get to this. But we're able to save some time by using xenon as our place of starting. We don't use anything besides noble gases for these shortcuts. So even though, yeah, lead has all this extra stuff that we have to worry about, we still have to do it that way. So we can only use the noble gases as shortcuts. And one more thing, for something like neon, we have to say the previous noble gas. We don't say just neon. We'll have to say 2s2, 2p6. But for sodium, which is one more, then we can say, oh, yes, neon, 3s1. No problem. And so it's a little bit easier this way, right? So this just will take some practice. Use your periodic table, make many photocopies of it, print out a lot of them, because you'll be writing on them a lot. And so these electron configurations, we can also talk about specific electrons within them. If we say, let's take a look at this lead example. We said that xenon, and I'm going to draw the boxes out so we can see. Wow, didn't need such a big box. Six. Ugh. Why did I choose lead? 1, 2, 3, 4. The 5D, and then we have our p orbitals here. So leads. Gosh, why did I choose this? Okay. It's got all these filled. I'm just going to go ahead and fill them off, and then 2 there. If we wanted to talk about any of these electrons, remember that this number up here, in front of it, these two numbers correspond with N and L. And ML for this is 0, but for here, this would be our various MLs. We typically just do these as negative through positive. And we could talk about any of these electrons. I want to talk about this one right here. Oh, I just destroyed it. Okay, well, I want to talk about the purple electron. What quantum numbers does the purple electron have? Well, let's take a look at it. If you look at 5D, remember that for a D orbital, L is 2, right? So the letters S is for 0, P is for 1, D is for 2, and F is for 3 for L. We would say for this one, because it's in this box, That's ml of 0. And because it's an up-pointing one, we say that the spin number is positive 1/2. And so these would be the quantum numbers necessary to tell us about that specific electron. No other has these 4 quantum numbers. No other electron can be labeled this way. So using these quantum numbers, we can talk very specifically about one exact electron. We can say, oh, well, I'm talking about the one where n is 5, l is 2, ml 0, ms is positive 1/2. And that's an electron in 5d. It happens to be in the middle of the box here. ML and MS are less relevant, but 5D is more important because they're degenerate, right? So all the D subshells are equal energy to each other. So being able to identify something using the quantum numbers is very useful for us. And some of your homework does talk about this. So um, it's definitely worth practicing. And so if we were to say, how about let's do another one. How about we do the orange electron? Let's do this one down here. This orange one, the orange one here, well, it's got n equals 4, l equals 3, ml equals 3, and ms equals negative 1/2. Because it's pointing down. That's the convention we use. So we can describe any electron using these. And let's do this. Color haven't I used? This red one. We're going to make this one angry. I have to be very careful here. I'm just going to write over it. This red electron, I don't know where I'm going to write this. Here, I'll write it here. The red one, n equals 6, l equals 1, it's a p, and ml equals 0, and ms equals positive 1/2, I think, yeah. So you see here, we can talk about any electron specifically by looking at this. And this idea that no two can have the same quantum numbers is called the Pauli exclusion principle. So nothing can have the same 4 quantum numbers within a particular atom. So when we're talking about something with n equals 4, l equals 3, ml 3, and ms equals negative 1/2, there's only one electron that has those 4. So we're very specific about which ones we're looking at. And so this is all very useful stuff. So if we're saying, okay, well, for n equals, here, let's do some random ones. How about n equals 3, l equals 1. What does this refer to? Well, this refers to the 3p orbital. And if I say, I mean, the other ones are kind of less important, but these ones are the big ones. So this you should be able to definitely do. The ML and MS are a little bit more arbitrary, but they are still important for us to distinguish that no two electrons can have the same quantum numbers. Even the ones in the same box, they would just have different MS values, right? One is spinning up, one is spinning down. And so we have all these options. All right, so that is all of chapter 6. We're going to see trends now on these in the next chapter. So, Ray, we're going to see next week, we're going to talk about periodic trends. We're going to see how the periodic table is arranged. So besides all this fun stuff, we'll see all that. And yeah, so we'll have some homework on this. I think y'all got an exam on Monday on uh, what's chapter 4? Aqueous reactions and then thermochemistry. So don't forget that. And yeah, we'll go from there. So as always, questions come up, put them in Discord. I'll be happy to take a look at them. Alrighty, so best of luck. Enjoy your weekends. Study well. And we'll see you next week. All right, take care.